We'll wait for a few minutes for others to join.
Okay, sir. Okay. Okay.
All right. So welcome to the week 10 tutorial for the course IC Engines and Gas Turbine. I hope everyone is uh, regular to the lecture videos by the professor as well as to the tutorials and submitting the assignments on time. So
This is the
in,
last tutorial, sir.
no, this is not the last tutorial. We
Yeah,
have
no,
we have few
no.
more tutorials left,
Okay, okay, okay.
and uh, I was saying that if someone is not able to watch the video, they can directly check on my YouTube channel, Nptel with Varnit, where all the videos are there for the corresponding course. And in each video description, there is a link to the G Drive link for the PDF notes. All right. So in the previous tutorial, we had started with the performance, improving the performance of the gas turbine. So there were three ways. One was regeneration, second was reheating, and the third one we will discuss today. That is intercooling with gas turbine. So let me share my screen and I hope my screen is visible.
Yeah, sir. Visible.
Oh, okay, thank you. All right, so let us start. The topic is case three. Let me first write case three. That is intercooling with gas turbine. So here what we will do, we will reduce the compressor work. So it is another way of improving the work net output by reducing the compressor work. It is another way of improving work net output by reducing compressor work. All right. So let me first make the schematic diagram to show. So we have compressor from where at the inlet at 1 and the outlet is at 2. Then it is passed through an intercooler. intercooler. Okay. Intercooler. Okay. Then the exit of the, so this is 2. Exit of the intercooler is again passed through another compressor. This was compressor 1. This is compressor 2. And the exit is at 3. Then exit of compressor is at 4. So let us make this with 4. Then it is passed through the combustion chamber, CC, where the heat is being supplied. Then the exit of this is passed through the turbine. And finally the 6th stage output. And this was the 5th. Okay. So what we are doing with the help of this intercooler, we have increased the pressure and temperature from the compressor 1. Okay. Then we have passed through the intercooler where we are decreasing the temperature but at the same pressure. Okay, of the fluid, of the working fluid. So we are decreasing the temperature. Someone has joined. Lobby. Okay. So we have decreased the temp. Am I audible? Hello. Am I audible? Santosh, can you confirm? Okay. So we have basically what we are doing, we are decreasing the temperature of the compressor 1 outlet, but at the same pressure. And then we are again increasing the pressure by passing it through compressor 2, and then we are providing the heat in the combustion chamber and finally passing it through a turbine where work output is we are getting. Okay, so intercooler is used because temperature is decreased at the constant pressure. Let me write. Because temperature is decreased at constant pressure, if at any point of time I'm not audible or my screen is not visible, then let me know, so that cross it doesn't cross metallurgical conditions. Okay, so that the blade doesn't melt off. Okay, so let us make the temperature entropy plot for this. Temperature entropy. So first stage is that we are passing it through a compressor from 1 to 2. Okay, then we are decreasing the temperature. Okay, so we are decreasing the temperature, but at same pressure we are not reducing. Okay, because we have passed through a compressor, and then again we are increasing the pressure. Okay, as well as temperature passing through the another compressor 3 and 4. Then we are passing it through a combustion chamber, that is your 5th stage, and then we are passing it through the turbine 6th stage, and finally back to your, let me make it again. Okay, 6, and finally expanding it back to original state 1, the working fluid. Okay, so here heat is being supplied at this point, Q supplied in the combustion chamber. the temperature of 1 and temperature of 3 and temperature of 2 and temperature of 4 are tried to maintain equal for perfect intercooling. Okay, for perfect intercooling. For perfect intercooling. Okay, then let me also write the pressure of 1 and 6 is equal and will be the lowest pressure. Similarly, the pressure of 4 and 5 will be equal and equal to highest pressure, EH, and 2 and 3 are equal here. Pressure 2 is equal to pressure 3, and let us say it is intermediate pressure. Okay, intermediate pressure. If intercooling wouldn't have been there, then how would your cycle look like? Instead of going from 1 to 2 and 2 to 3, it would have directly went to 1 to 2 dash. So original cycle would have been like 1, 2 dash, 5, 6, but current cycle is different. So let us again compare both of them for work net outputs and different mean heat supplied and work done by compressor, turbine, mean effective pressure, efficiencies, TMA, TMR, Q rejection, and so on. So let me write. I hope this much is clear. Am I audible? Hello.
You are audible. You are audible.
So the first is 1, 2 dash 5, 6, and 1. This would have been the original case of the gas turbine. But with intercooling, our cycle looks like 1, 2, 3, 4, 5, 6. So this is intercooling. So originally, the work by the turbine would have been only H5n minus H6. Okay, this would have been the work by the turbine, H5 minus H6. And here also, the turbine work will be remaining same, H5 minus H6. Second, the work by the compressor originally would have been between this H2 dash minus H1. Okay. H2 dash minus H1. But here, the work by compressor is now 1 to 2 and 3 to 4 because two compressors are there. Okay. 1 to 2 H2 minus H1 plus S3 minus H1. Okay. But the question is, what the surprising thing is that the work net is decreased. You might see that two terms are here, and it might seem visible like that the work by the compressor has increased because two compressors are used. But in actual sense, the engineering sense is that the work net has been decreased. Let us understand why. First, let us understand the reason behind it. Okay. Let us make the pressure volume plot for it. Okay. To understand. Pressure volume plot. Pressure volume. If I wanted to increase the pressure from 1 to 2 dash originally, how would have it look like? This is 2 dash. This is 1. Okay. So the pressure would have increased and volume would have decreased. Let me again make like this. 1, 2 dash. But now what we are doing, we are increasing the pressure from 1 to 2, first of all, till here. Okay. We are not increasing to higher pressure till 2 dash. We are increasing directly. We are not doing it directly. We are doing it in two stages. First, we are increasing from 1 to 2. Okay. Then at constant pressure, we are increasing the temperature. So at constant pressure, that is 2 to 3, the constant pressure was maintained and temperature was increased. And then from 3 to 4, the pressure was increased to 2 dash, till 2 dash. Okay. So let me again make that till 3 to 4. So the pressure 4. So this pressure is equal to this. So P2 dash is equal to P4. Okay. So eventually we have increased the pressure in 2 stages, not directly. And when we have increased the pressure, the work done has decreased. Why? So if you go by from the thermodynamics, in the thermodynamics, it is an open system device, because here mass as well as energy exchange is happening. Energy means work here in the compressor. Compressor is an open system device where mass as well as energy is being exchanged. So for an open system device, the net work output is nothing but work is equal to minus VDP. Okay, minus VDP. That means you are taking the area under the graph, and your axis will be defined from this region to this region. So change in the pressure. So this will be your area under the graph for an open system. You are seeing at same volume how the pressure has been changed. Okay. So this is your area under the graph. Earlier, when, if you would have seen, when we have directly taken from 1 to 2 dash, then your area under the graph would have been this. Okay. So that means you have reduced this much amount of area here. This amount of area is not here for our blue lines. That is your intercooling. So this, for same, we are saving the work by the intercooling. We have graphically seen that for this open system device, this much area is being reduced by the intercooling. Okay. So let me frame this in a better sense. So we can say that this much amount of area we have saving work by intercooling. Okay. So though it might have seemed like the work by the compressor have increased to reach the same pressure as 2 dash for 4, but in actual sense, the area under the graph has been reduced. And let us see from the mathematical sense also. This is for open system. When we say that from the ideal gas law, because we have assumed that in the assumptions in the first lecture of the gas turbine, okay, that was week 7 or hopefully week 7. Okay, so we say that we are using the ideal gas, that is your air is treated as an ideal gas. So that means your here volume is, you can say that for the same work output, volume is directly proportional to temperature. And when you are doing the intercooling, basically you are decreasing the temperature. You are decreasing the temperature. That means you are decreasing your volume. So when you are decreasing your volume, that means by intercooling, you are decreasing this term. Okay. So your work net is also decreasing. Okay. So let me write this term here in a better sense. Let me drag it above. So this implies your work is nothing but negative of VDP. Okay. And you have decreased this volume. So that means your work net has also been decreased. Okay. So with intercooling, your net area of the work is this much only. Okay. All right. All right. So let us come to the next third point. Third point is your work net. So that is work done by turbine minus work done by compressor. And here your work net is work done by turbine minus work done by compressor. And you have reduced the work done by compressor. So work done by net work has also been increased, sorry, has been increased because you have reduced the compressor. So you get more amount of work. So compressor work decrease, work net increase. But now heat supplied is increased here. Heat supplied, why it has been increased? Let us see in the graph. If you would have seen earlier from 1 to 2 dash, this cycle would have been there. Then the heat supplied was from 5 to 2 dash. Okay. But now you are doing the intercooling. You are reducing the temperature till here. Now your heat supplied is from 4 to 5. So from earlier, this, you have increased the heat supplied. Okay. You have increased the heat supplied. Someone is trying to join. Let me see. Yeah. Okay. So we can say that our heat supplied has been reduced. So let me write here. The heat supplied has been, increased. Okay. Next point will be your heat rejection will also be increased. Heat rejection, QR, will also increase. Why? Because earlier your heat was rejecting from only in original cycle 6 to 1. But now your heat is been rejecting 6 to 1 plus 2 to 3 as well. Okay. So heat rejection is also increased. Okay. Now, next point, let me write here since 6 to 2 plus 2 to 3. Okay. Then volumetric mean effective pressure has also been decreased. Okay. Mean effective pressure has also been decreased. Okay. Similarly, same, because earlier the pressure was from 1 to 2 dash. Now you are going from 1 to 2, then 3 to 4. If you will do the mean of two things, it's going to decrease eventually. So if mean effective P mean is decreased, eventually pressure ratio has decreased also. Because earlier the pressure ratio was from 1 to 2 dash. Now the pressure ratio is from 1 to 2, then 3 to 4. So pressure ratio from 2 to 1 and 3 to 4 is lesser than 2 dash to 1. So volumetric efficiency is also going to decrease. Sorry, volumetric, not volumetric. The efficiency of the cycle is also going to decrease since pressure ratio will decrease. Then mean addition temperature is also going to decrease, because earlier your temperature was, you have cooled down. Earlier your temperature was from 1 to 2 dash. Okay. But now you are doing from 1 to 2 and 3 to 4. You're eventually reducing the temperature by providing an intercooler. And mean rejection temperature is also going to decrease, because you are going to again take from 6 to 1 and 2 to 3. Rejection is happening low at a lower temperature as well here. That's why. Okay. All right. So let me again add one note here, that scope of regeneration, as we did for the case of reheating, again regeneration can use here as well. So note, the scope of regeneration increases with use of intercooling. Therefore, it is coupled generally with the regeneration. Intercooling is coupled with, is generally coupled regeneration. Okay. Now let us come to the point where we will see condition for minimum work output with perfect intercooling, as we saw for perfect reheating also. Okay, so I have said now here that for perfect intercooling, so conditions will be same as the reheating. So we won't go in the proof. We will just write it down directly. Conditions for minimum work output. You want to do the proof? Take it as a home assignment, that you have to do the minimum work output. You have to differentiate the network output with respect to the variable unknown in terms of higher and lower. Okay, with same as we did for the last tutorial in reheating, with Perfect. Intercooling. So here the first condition is the temperatures of T1 is equal to T3. Second condition, again, intermediate pressure will be a product of under root of P higher and P lower. Okay. Third, the work done by compressor 1 and work done by compressor 2 should be equal. And fourth, temperature 2 is equal to temperature 4. Okay. And these are the same as earlier. The turbine work was same, here compressor work was same. So I'll give you a very good question now, and it covers everything of the performance characteristics. And I'll give you some ample amount of time to do. But honestly, do this. You will understand each and every concept. Okay. A single question will be mere enough to cover all these topics. So let us do one question. If you have any doubts, please ask me right now. Do you have any doubts? Yes or no? Santosh, Mridula, any doubts? Or I'm not audible? Okay. Let's come back. A regenerative reheat cycle reheat cycle. So reheat and regeneration both are taken. Reheat cycle has air entering at 1 bar, 300 Kelvin, 1 bar and 300 Kelvin. Something uh, regenerative 1 bar 300 Kelvin. Into compressor having intercooling between two-stage compressor, air leaving the first stage of compressor. So that means you are doing intercooling also, regeneration also, reheating also. All the three things are being done here. Air leaving first stage compressor is cooled up to 290 Kelvin and 4 bar pressure in intercooler and subsequently compressed to 8 bar. And subsequently compressed to 8 bar. Compressed air leaving second compressor passes through a regenerator having effectiveness of 80%. Subsequently, combustion produces Subsequently, combustion produces 1300 Kelvin at inlet of turbine having expansion up to 4 bar. And then reheated up to 1300 Kelvin. So that means perfect heating is here. And reheated 1300 Kelvin before being expanded up to 1 bar. Exhaust from turbine passes through regenerator. So the question might seem a big, but everything is given in the question. Passes through regenerator. Consider compression and expansion to be isentropic. Expansion and compression to be isentropic. Suppose if non-isentropic would have been there, then extra calculation would also be there. Isentropic. Calculate overall efficiency. Okay, so do this question. Take few minutes.
Sir,
Yes.
sir, I have one doubt in converting converting Kelvin to Celsius or Celsius to Kelvin. What type
So
of
degree Celsius is, suppose you have
Celsius to, for
20
example,
Celsius.
air enter into air
Let me
20 degrees Celsius. It was converted to 20 plus 273 equal to 293 degree Kelvin. Sorry, Kelvin. So what type?
So what type? Hello, Santosh, you are not audible. I can't hear you. Yeah.
Uh, can you hear that?
Yes, yes, I can hear you. I can hear you now. Please unmute and speak.
Can I ask question?
Yes, yes, you can ask. So I was saying
At
the
what?
conversion is just you add 273 to the degree Celsius temperature. You will get in Kelvin. Okay.
Okay, 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 sir. What types of question we have to convert Celsius to Kelvin, sir?
So generally, you have to deal in Kelvin only. Okay. Always remember you have to deal in the SI
Okay,
unit form. Okay.
okay. Celsius is Kelvin is SI unit of Celsius, sir.
Yes.
Okay, okay. Thank you,
Kelvin
sir.
is
Thank you.
in the SI unit. Yes. So please do this question. Take some time, but you will have a good understanding for this question.
Okay, okay. Thank you.
Have you done or still doing?
Wait a minute, sir. Wait a minute. I'm working.
Okay. Yeah. Any doubts in the question? It's a very easy question. Then you will do. Everything is given in the question. That's why it's a lengthy question to see. Take more few minutes. I'll give the time for doing this question. Done? Or you need more time? Santosh, you need more time or should I start the solution? Okay, I'll give a few more minutes. Okay, so let's solve it. Santosh, you have done? Did you got the answer? You have to unmute and tell me. You're muted. Did you got the overall efficiency? I can't hear you actually. You are still muted. Okay. All right. So let us solve this question now. So let me test this moment. Yes, Srinath, if you have any doubts. Okay. All right. So let us solve it. So we are given a regenerative, reheating, and intercool cycle. Okay. So all the three things are there, and it is a case of perfect reheating. Okay, not perfect intercooling, perfect reheating. So first, it is said that in the question, the air is entering at 1 bar and 300 Kelvin into compressor, having the intercooling between two-stage compressor. Air is leaving the first stage at 290 Kelvin. It entered at 300, but it reduced to 290 Kelvin. Okay. So let us make the plot for it. Always start by making the plot. Then you will understand in a very having a very clear picture. Temperature entropy plot. So first stage compression. So from 1 to 2, isentropic compression is given. It is said that. So 1 is at 300 Kelvin, entered at 300 Kelvin, and then it was passed through the first stage and it reached to 290 Kelvin. Okay, 290 Kelvin. So this is your stage 3. Okay. Then it again increased. Let us say we don't know because it's not perfect intercooling. So let us say it increased the pressure till here. 4. We have to calculate that pressure. Then it is said that compressor is cooled up to 290 and 4 bar pressure in intercooler and subsequently compressed to 8 bar. Okay, so from 4 bar it is increased to 8 bar. So from 4 bar to 8 bar. Okay, then it is said that it is passes through a regenerator with 80% effectiveness. Okay, so regeneration will be there eventually. So let us say this is a point A as per the regeneration. And then it is further passed through 1300 Kelvin through the combustion process. Okay, it will reaches till 1300 Kelvin here. Let us say this is stage 5 and it is 1300 Kelvin. And then it is said that inlet of turbine having expansion up to 4 bar and reheated up to 1300 again. So it is perfect case of, let us say, it is again first reducing the pressure by the expansion and then again reheated till 1300 Kelvin. So this is stage 6, then stage 7, and again expanded. Okay, we don't know what is its temperature. Okay, so we can't say it has perfect reheating as well. We just know four conditions should be satisfied. Okay, let us see. And then finally it is expanded through the second turbine and reaching the stage 1. Okay, so this is your whole cycle. It looks like this. Okay, so the cycle looks like this. Someone is trying to join. Okay, so we have plotted the cycle. We'll write again the pressure, given pressure values and the temperature values. So P1 is given to you, which is again eventually equal to P8 here. Okay, and that is given to you as 1 bar. Okay. Then P2 and P3 is given to you from the first stage compression. That is equal to 4 bar. Then from the second stage compression, P4 and P5 is given to you. That is 8 bar. Okay. Then expansion pressure is given to you between the turbines. P6 is equal to P7. That is again 4 bar. Effectiveness of the regenerator is given to you. That is 0.8. Okay. All right. And temperatures are given that I have marked on the plot itself. So let us first get the individual temperatures. We know the first T1 temperature, we don't know T2 temperature. So, and gamma will remain 1.4 only. Okay. So T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma. Using this relation, you have T1 given as 300. Okay. P2 by P1. So P2 by P1 is 4 by 1. That is 4 to the power of 0.4 by 1.4. So from here, your temperature 2 will come out to be 445.79 Kelvin. Okay, this is your temperature 2. Similarly, using this concept, T4 by T3 is equal to P4 by P3 to the power of 0.4 by 1.4. Again, someone is trying to join me. See. Okay. So P4 by P3 again is given to you. P4 by P3, 4, 8 by 4, that is 2. Let me write. T4, you don't know. T3, you know 290 Kelvin. 8 by 4 to the power of 0.4 by 1.4. So from here, your T4 will come out to be 353.151 Kelvin. Okay. So you got T2, you got T4. All right. Now again, T7, you don't know T6 and T5. Okay. So again, let us use the relation T6 by T5 is equal to P6 by P5 to the power of 0.4 by 1.4. So again, T6 and T5 is 1300. P6 by P5, again 8 by 4. So 4 by 8, sorry. P6 is 4 and P5 is 8 to the power of 0.4 by 1.4. So T6 will come out to be 1066.43 Kelvin. So you got T6 also. Okay. Now between T7 and T8, again, we can apply this. T8 by T7 is equal to P8 by P7 to the power of 0.4 by 1.4. So T8 you don't know, but T7 is again 1300. P8 and P7. So this is P8 and this is P7. So 1 by 4. 1 by 4 to the power of 0.4 by 1.4. So from here, your T8 comes out to be 874.83. Now you have all the temperatures except TA and T, or except the TA, okay, this temperature of the regenerator. You don't know this temperature. Let us get that TA as well. Someone is there. Okay. All right. So T8 we have got. Now, what is the effectiveness given to you? Effectiveness of a regenerator is 0.8, and that is nothing but how much the temperature has actually increased to the maximum temperature it would have increased. So TA minus T4 from here to here, and it would have increased from T A T. How what would have it come? T8 minus T4. Okay, here too. Okay, all right. So let us write it down. T8, how much maximum it would have been increased. So TA you don't know, T4 you know from here, 353.51. T8 you know 874.83, and T4 again 353.5. Okay. So from here, your TA will come out. Okay. And you can use this TA in the efficiency now. So efficiency is nothing but work net by cube supplied. Okay. And work net is nothing but turbine work. Two turbines are there between 5 and 6 and 7 and 8. So in terms of temperature, we can write, because it's a isentropic we are assuming. So enthalpy is directly a function of temperature itself. So, and enthalpy is in terms of temperature. So T5 minus T6 plus T7 minus T8. So these are turbine work minus compressor work. Two stage compression is given, T4 minus T3 plus T2 minus T1. And what is the heat supplied? Heat has been supplied between 5 and 8. That is between this to this. And again, between 6 and 7. Two times heat has been implied, given, supplied. Okay. So that is T5 minus TA plus T7 minus T6. Now you put all the values, all the temperatures you have calculated, and finally you will get your efficiency to be 58.9%. And this is your answer. Pretty simple question. Just to see the graph. Just by making the graph, we have been able to solve this question. Okay. We got all the temperatures. We have put all the temperatures and we got the efficiency. No formula required. Any doubts in this question, please ask at this point, because now will start with the topic compressor, individual component of the turbine, that is your compressor. Okay. If you have any doubts, please ask. We are done the gas turbine part. Now we will move to the compressors. That is the last topic, towards the last topic of the course. But here the compressor itself has multiple subtopics as well. If you have any doubts, please ask, or you can meanwhile think on this question once again. Okay. I'll just show you the plot. You will get to know. We have just used this expression only, T2 by T1, T higher by T lower is equal to T higher by P lower to the power of gamma minus 1 by this relation for every process, because it is given to be isentropic. Take a few minutes, I'll be back. And then we'll start with the compressor. Okay. If no one has any doubts, we can proceed further to the topic compressors. Compressor. What is the function of a compressor, basically? What is a compressor? So it is nothing but a mechanical device which is used to increase the pressure of a gas or vapors. Okay. It is a mechanical device. It doesn't increase, it does increase the pressure. It is a mechanical device used to increase the pressure of gas or vapors. What are different types of compressors available? So on the basis of principle of the operation, the different type of compressors are there. The first is on the basis of the principle of operation, that is positive displacement compressor, and other is rotary or dynamic compressor. Let me write types of compressor. First one, categorized on the basis of principle of operation. So here, the first one is positive displacement compressor. What are positive displacement? In this type of a compressor, pressure of the gas is increased by decreasing the volume in a confined cylinder. Basically, what we have seen in the IC engine. It's a positive displacement where the compression process happens in a confined space, okay, where you decrease the volume by compressing the fuel, air fuel mixture, and you increase the pressure by positively displacing the working fluid to a lower volume. Okay. So let me write here. In this type of compressor, pressure of gas is increased by decreasing volume in a confined cylinder. That is, the rise in pressure is obtained by positively displacing the working fluid to lower volume. Okay. Example, reciprocating compressor. Okay. The second is rotary or dynamic compressor. What happens here? In this, the kinetic energy is imported to the gas by rotating the element called as rotor. And this high kinetic energy, so you have a working fluid and the rotor is rotating at a very high speed, having a higher kinetic energy. It provides that kinetic energy to the working fluid as well. Okay, that is your gas. And this high kinetic energy is then converted into the pressure rise in the diffuser. In the diffuser. So basically, you are increasing the pressure on the basis of dynamic action. Okay. So here, like centrifugal compressors are there, axial flow compressors are there. Okay. So we will go into the study of each of these kind of compressors. Don't worry. There you will understand in a much better way. Okay. So let me write in this high kinetic energy is imparted to gas by rotating element called as rotor. And this high kinetic energy is converted into pressure rise in the diffuser. Therefore, rise in pressure is obtained by obtained due to dynamic action. Example, centrifugal or axial flow compressor. Okay. So these were on the basis of the first category. Now the other category on the basis of pressure developed. So if there is a less than 10 bar, pressure is increased less than 10 bar, then it's a low pressure compressor. Between 10 to 80, it's a medium pressure compressor. And greater than 80 bars, it is a high pressure compressor. So let me write on the second category on the basis of pressure developed. Less than 10 bar, low pressure compressor. Between 10 to 80 bars, it's medium pressure compressor. And third is greater than 80 bars, high pressure compressor. The third category is on the basis of volume handling capacity. On the basis of volume handling capacity. So the first one again, less than 9 meter cube per minute, small handling capacity compressor. Between 9 to 3000, medium, and greater than 3000, large. Less than 9 meter cube per minute, it is small handling capacity. Between 9 to 3000, medium handling capacity, and greater than 3000 meter cube per minute, large handling capacity compressors. Okay. Now the fourth category is based on pressure rise. Okay. It was pressure developed and based on pressure rise. Okay. How much pressure can be raised? Fourth, on the basis of pressure rise. So the first is your fans are there, where only up to 1.1 bar. Atmospheric is 1 bar and it is just 1.1 bar. So fans up to 1.1 bar. Second, blowers are there, where 1.1 to 2.3 bars. Third is your actual compressors, that is above 2.3. Compressors above 2.3. Okay. So we can make a small table for pressure capacity and volume handling capacity. Okay. Pressure handling capacity and volume handling capacity between the category. Okay. Between these categories. So let me make a table here. Okay. So the first is reciprocating and the other is rotary. So pressure handling, capacity, and volume handling capacity. So the reciprocating compressors are able to produce high pressure handling capacity but low volume handling. Okay. So if you see it's in a confined cylinder, that's why confined space. So low volume it can handle, but it can increase your pressure very high. Whereas rotary have low pressure handling capacity but high volume handling capacity because there is no restriction on the space here. Okay. All right. Now let's come to finally the reciprocating compressors and let's study them in detail. Reciprocating compressor. So they are used to produce very high pressure, even up to 1000 bars, which is not possible to obtain with the help of rotary compressors. But the volume delivered is very less, and there is a problem of intermittent supply and poor efficiencies. Okay, so let me write point by point. They are used to produce very high pressure Hello, am I audible now? Santosh, Ravindran, can you please confirm me? Am I audible? Hello, Santosh, can you unmute yourself and tell me, am I audible or not? Or Ratish? Because I don't know, I was stuck in share screen. Okay. . Okay, I think my screen is visible now. Yeah, I don't know what has happened here. This was okay. So I was telling in the last on the basis of high pressure, fan, blower, and compressor, and for reciprocating and rotary, reciprocating have a high pressure capacity handling and low volumetric handling capacity, whereas rotary has low pressure handling capacity and high volumetric handling capacity. Okay. So I was talking about the reciprocating compressors. They are used to produce very high pressure, used to produce very high pressure, even up to 1000 bars, which is not possible to obtain with help of rotary compressor. But the volume delivered is very less. And there is a problem of intermittent supply. And poor efficiency. Next point. So it consists of two walls, one on the section side and one on the discharge side, as we have seen in the IC engines. And these are the automatic walls operated due to pressure difference across them. Okay. And they are generally plate type or disc type walls. And these type of compressor are generally used in air conditioning, refrigeration system, air filling stations, etc. It consists of two walls, one on suction side and other on discharge side. Just hold on. Okay. One on suction side and other on discharge side. And these are automatic valves operated due to pressure difference across them. Generally, plate type or disc type valves are used. These type of compressor are generally used in air conditioning, refrigeration system, air filling stations, etc. So what are the advantages and disadvantages? So the advantages first, they are able to produce very high pressure and they require less space and low cost. Okay, advantages. First is very high pressure can be developed. Second, less space required and low cost. What are the disadvantages? They provide intermittent supply, not continuous basically. Volume handling capacity is low. Less RPM, so can't be coupled with a turbine in power plants. They have balancing issues. Mechanical losses are there due to sliding motion during the reciprocation. Okay. Disadvantages. Intermittent supply. Low volume handling capacity. Third, less RPM, so can't be coupled with a turbine in power plants. Fourth, balancing issues, produces vibrations and noise. Fifth, mechanical losses are high due to sliding motion. Okay. Now let us see the compressor where we are able to where we are giving the work input to the compressor without the clearance volume. There is no clearance volume. As we used to have in an IC engine, we used to have a clearance volume so that walls doesn't hit. But suppose if the clearance volume is not there, then how the work input will be calculated? So let us come to the case one. Work input to compressor without clearance volume. Okay. So let us draw pressure volume plot. For getting the work, we need to see what is the pressure volume plot. Okay. And it's an open system device. Compressor has both energy as well as mass interaction taking place. Open system device. And as I've just told, for an open system device, you plot the area under the graph on the pressure axis. Okay. So let us make the pressure volume, pressure and volume. So initially you had a pressure of P1, okay, lower pressure. And you are Work was done by the system during this suction process, as we used to do in the IC engine. Suction process is happening. So at pressure P1, suction is happening, and let us say it is stage 0. There is no clearance volume. Okay, there is no clearance volume. So you are starting directly from here only. And let us say it is stage 0, and it reached stage 1. Okay, from here. Then pressure was increased and volume was decreased. Okay, let us say by any law, polytropic law, PV raised to power n. Okay, it followed, and pressure was increased and volume was decreased. So let us say the law was PV raised to power n is equal to constant. Okay, polytropic law. And this is stage 2. It has reached by increasing the pressure and decreasing the volume. Okay, so volume here is V1, and here the volume is V2. Okay, you have decreased the volume. And finally, the discharge is happening at a constant pressure from here. No clearance volume is there. And you reach the stage at P2 is equal to P3. And this is your stage 3. Okay, stage 3. So here, how we will calculate the work for each process, let us see, from 0 to 1, 1 to 2, and 2 to 3. So from stage 0 to 1. So work done by the system. So anyone has joined? So working fluid is the system here for us. So what is the work done here? That is your VDP. That is change in the volume, sorry, PdV from the suction process. Okay, there is a change in the volume. So at a constant pressure, the volume has been changed. Work done by system during suction is nothing but P into V final minus V initial. So what is the pressure? Pressure is P1 from 0 to 1, and V final is V1 from initial V naught. That was 0 itself. Okay, so that was 0 only. So that is P1 V1 because it is 0. No clearance volume is there. Okay. P1 V1. Then from 1 to 2, it's a polytropic process. From 1 to stage 2, work done on the system, work done on system during compression, work done on system during compression. So if you see in thermodynamics, for an open system device, the work done is nothing but P1 V1 minus P2 V2 by n minus 1. Okay, P1 V1. So all of these are we have been come from the thermodynamics only. So okay, so work done for process by process. Work done overall. This is an open system device, but we are going process by process. So we are seeing the it, taking them as a closed system work happening. So it is P1 V1 minus P2 V2 by n minus 1. Third is from 2 to 3. That is your discharge. Work done on the system during discharge. Work done on system during discharge. So from 2 to 3, pressure is remaining same, but the volume is again changing. That is, so one is showing. Okay. Work done during the discharge is nothing but PV final minus V initial. So pressure is nothing but P2. V final is 0 at 3 and V initial was V2. So it is minus P2, 2. Okay, minus P2. So net work will be from 0 to 1, 1 to 2, 2 to 3. All the work you have to add. So work net is P1 V1 plus P1 V1 minus P2 V2 by N minus 1 minus P2 V2. Add all of them and finally you will, on simplifying, you will get that N minus 1 times P1 V1 minus P2 V2. Okay. And this is nothing but your closed system work. Okay. And this is equal to work of open system, that is net work. Okay. Work of open system is n time of work of closed system. Okay. So you can write work of open is n time of work of closed. Okay. If you don't know how this expression comes, you can see in my thermodynamics videos, lecture videos, those tutorial videos. I have explained each and everything on my YouTube channel, Nptel with Varnit. Okay. All these open system and closed system I have dealt with. So here we have got that work of open system is equal to n times of work of closed. So what is the net work input here? Again, I'll write here. Work input is n over n minus 1 times P2 V2, n over n minus 1 times P2 V2 minus P1 V1. Okay. And if I take P1 V1 common from here, it will be P2 V2 by P1 V1 minus 1. Okay. And we know that from this law, PV raised to power n is equal to constant, that P1 by P2 is equal to the power of 1 by n is equal to V2 by V1. Again, all these things have been derived in thermodynamics. I'm directly taking from there. Okay. So I can use this V2 by V1 from here. Okay. And put in terms of pressure. So that will be work input is nothing but n by n minus 1 times P1 V1 into P2 by P1 multiply with P1 by P2 to the power of 1 by n minus 1. And finally, your expression will come out to be, on simplifying, n by n minus 1 times P1 V1 into P2 by P1 power n minus 1 by n minus 1. And the units are joule per cycle. This is your final expression for work input for a compressor for the case if the volumetric, if the clearance volume is 0. Okay, there is no clearance. Okay, and if the cycle is operating, the whole cycle is operating at n rpm, as we have seen in the IC engines, we will multiply the work input with n by 60 to convert in joule per second, not joule per cycle. Then let me write it as a note. If cycle operates at n rpm, n revolutions per minute, then you will get the power input as work input into n by 60, and this will come out to be units joule per second. Okay, the power input will be this. Now coming to the case 2. The case 2 is work input to the compressor with the clearance volume. What if the clearance volume is involved? Let me write. Case 2, work input to compressor with clearance volume. Why clearance volume is given, as we have seen in the IC engines also, so that the ball should not strike with the piston there. Okay, as we have seen there. Similar is the reason here. So if clearance volume is not there, how the plot will look like? Let me show. Pressure volume plot. Okay. So from 1 to 2, your processes is from compression. Let us say polytropic compression is happening. 1 to 2. PV raised to the n is equal to constant. Okay. Then at same pressure, the clearance is there. Okay. So that's why we have stage 3. At same pressure, discharge is happening. Okay. Exhaust is happening. Expansion is happening now from 3 to 4. And finally, suction happens from 4 to 1. Okay. So suction happens from 4 to 1, 1 to 2 compression, 2 to 3 exhaust, 3 to 4 expansion, and 4 to 1 again suction. Okay. So let me make the volumes here. So this is V1 and this is V3. That is your clearance volume. V3 or which is equal to VC, clearance volume. Okay. Clearance volume. And the pressures will be P2 is equal to P3. That is your P higher, P higher. And here the pressure will be P1 is equal to P4 is equal to P lower. So clearance volume has been involved here. So again, we have derived the compressor work that is from 1 to 2 already. But during the expansion, the stroke is going back because it's an intermittent supply. What will be the work? Again, it's an open system process is going to come. So we'll write it directly. So work from 3 to 4 will come out to be n by n minus 1 times P3V3 minus P4. Similar as that. And again, we will take out P4V4 from it. So it will be P3V3 by P4V4 minus 1. And again, you will do the same. That is the ratio P4 by P3 is V3 by V4 to the power of 1 by n here. And you will put this here for V3 by V4. And you will get your final expression from 3 to 4 as n by n minus 1 times, sorry, P4V4 into P3 by P4 power n minus 1 by n minus 1. Okay. So total work output will be from 1 to 2 and 3 to 4. So 1 to 2 is a work absorbing process, 3 to 4 is an expanding process. So there will be a difference from 1 to 2 minus 3 to 4. Okay. So net total work output is total work input is basically work from 1 to 2 minus work from 3 to 4. Okay. So n by n minus 1 P1 V1 times P2 by P1 power n minus 1 by n minus 1 minus n by n minus 1 times P4 V4 times P4, sorry, P3 by P4 power n minus 1 by n minus 1. Okay. And we can see that pressure of 2 and 3 is same as higher and pressure of 1 and 4 is same as lower. Okay. So we can say this to be equal to P1. Okay. And this to be equal to P2. So you can say that this term and this term is same and this term and this term will be same. Okay. P2 by P2. This not this whole term, sorry, because here V1 is there and V4 is here. Okay. So I'll take it out in terms of V1 minus V4. Let me simplify. Yeah. Okay. So it will be n by n minus 1 times P1 V1 minus V4 because volumes are not same, and P2 by P1 to the power of n minus 1 by n minus 4. Okay, all right. And V1 minus V4 was your actual volume. That is your swept volume, as we have seen in the IC engines again. Okay, so from V1 to V4, this was your actual volume that was swept because V3 was your clearance volume. Okay, so this is nothing but your V actual. V actual. Okay, all right. Let me write it as work input to the compressor. It's a final work input to the compressor. Okay. If I say that in this expression V4 is 0, there is no clearance volume, then it is same as that of the previous case, that was P1 V1 times the bracket values without the clearance volume. So just remember, you can remember this one. You just take V4 as 0, you will get the previous case. Okay. So we can say that if actual volume entering the compressor is same in both the cases, then there is no impact of the clearance volume. Let me write the note points here. First note is if actual volume entering in compressor is same in both the cases, both above cases, then there is no impact of clearance volume of clearance volume of clearance volume on work input. Okay, and mass entering and leaving the compressor is same here in the second case. Mass entering and leaving compressor are same. That is M1 minus M4 is nothing equal to M2 minus M3. Okay, always remember this. Now, if there is some clearance volume, eventually we will come with the volumetric efficiency of a reciprocating compressor. How efficient it can be. Okay, let us derive that. That's it. Volumetric efficiency of a reciprocating compressor. Okay. So there is an actual volume and there is a theoretical volume. So swept volume was from 1 to 4, and there was a theoretical volume from 1 to 3, which could have been there. So from here to here, there was a theoretical volume. Let me mark here. Theoretical, VTH. Okay. Actual was 1 to 4. So it is defined as the ratio of actual volume at entry of compressor to that of theoretical swept volume. It is defined as the ratio of actual volume at entry of compressor to that of theoretical swept volume. To that of theoretical swept volume. All the piston move from V3 to top dead center to bottom dead center, but actual volume, which was where the entry to the compressor was there from 1 to 4. Okay, so we can write it as volumetric efficiency as V1 minus V4. This is actual with that of V1 minus V3. So if I just in numerator add and subtract with V3 to get towards an expression, so I can say that we can write it as 1 plus V3 minus V4 by V1 minus V3. How? So V1 minus V3 we took together and it cancelled out from denominator. It got to be 1, and V3 minus V4 by V1 minus V3. That's how I have written. A simple mathematical manipulation. And we will separate here 1 plus V3 by V1 minus V3 minus V4 by V1 minus V3. We are separating them. Okay. We can say swept volume was from 1 to 3 and clearance volume was Vc. So this was your clearance volume Vc and this was your swept volume Vs, as we have seen. So this is your clearance ratio as we have seen the IC engines as well. So this is 1 plus C times 1 plus C minus, again here you can do the same. If you multiply with Vc by and divide by Vc, and this is nothing but your V swept. So this whole will be clearance volume, clearance ratio C. So this will be minus C times V4 by Vc, and Vc is nothing but your V3. Okay. All right. So this is your volumetric efficiency formula. And in terms of pressures, you can say that since V4 by V3 is P4 by P3 to the power of 1 by n, not P4, P3 by P4 to the power of 1 by n. Okay. And P3 was P higher and P4 was P lower to the power of 1 by n. Put this. Therefore, your volumetric efficiency comes out to be 1 plus C minus C times P higher by P lower to the power of 1 by n. And if I take out C common, 1 minus C times P higher by P lower to the power of 1 by n minus 1. This is your volumetric efficiency. Okay. This is your volumetric efficiency. If in this scenario, if your P higher by P lower ratio is 1, then 1 minus 1 is 0. Your volumetric efficiency will be equal to 1. That is your 100%. Okay. Which is not possible eventually. Second, if you increase the pressure ratio, if you increase this, eventually the volumetric efficiency is going to decrease. So I'm writing few points here in terms of note. First is, if P higher by P lower is equal to 1, this implies your volumetric efficiency is 100%. Second, if we increase P higher by P lower ratio, this implies your volumetric efficiency is going to decrease. Okay. If you are going to increase the clearance ratio, that is this, then again your volumetric efficiency is going to decrease. And if you are going to increase the polytropic index, if you increase this, then overall this will decrease, overall this expression will decrease, and your volumetric efficiency will increase. Okay. Decreases. And last point, if polytropic index is increased, that is you go from a tri to di or monoatomic gas, your volumetric efficiency is going to decrease for a monoatomic gas. For a monoatomic gas, the polytropic index is highest. We have seen this thing in the IC engine part. Okay, so your efficiency is going to increase. So that's why from IC engine perspective, you can understand that using the monoatomic gas scenario reduces the knocking or increasing the knocking processes we have seen there. But here, in the terms of compressor, they increases the volumetric efficiencies. Okay, so there is a need of clearance volume. Why? Because your piston cylinder, the piston should not hit with the walls. Okay, and there should be some space for thermal expansion as well, as we have seen already in the IC engines as well. Okay, so similarity is there here and there. Okay, I think we can end this session here, and all these PDF notes and the recording of this session will be available in the form of a Google Sheet, which will be sent to you by a uh, NPTEL team, those who have registered in the course, those who are watching directly from the YouTube. So you can search, those who are not registered are watching from the YouTube. So they can search all these videos on my YouTube channel that is named as NPTEL with Varnit. My name is Varnit Kapoor. And in the playlist section for the corresponding course, IC Engine and Gas Turbine, you can see all the week-wise videos. And in each video description, there is a link for the Google Drive where all the PDF notes are being uploaded, okay, for each week. So I'll see you on the next Tuesday, same time, 6 to 8 p.m. Till then, bye bye.